Have you ever stared at an organic chemistry reaction and felt like you were looking at, I don't know, a secret code?
Hmm.
Or maybe trying to understand a story written in a language you hadn't quite mastered?
Oh, definitely. It can feel that way sometimes.
Well, today we're unlocking that code. We're taking a deep dive into what's literally called the key to your success in organic chemistry reaction mechanisms.
Hmm.
Specifically, we're exploring Chapter 8 from Organic Chemistry as a Second Language. First semester topics, 4th ed.
That's right. And mechanisms are truly central because they don't just tell you what happens in a reaction.
Right.
They tell you how it happens. You know those curved arrows you've seen?
Yeah.
They're not just abstract symbols. They illustrate the real, actual flow of electrons.
Mm.
And once you grasp this, reactions stop being just like isolated facts to memorize. They really start to make sense because they all follow what the chapter calls a small handful of simple principles.
And our mission for this deep dive is exactly that. To, pull out the most important nuggets of knowledge from this chapter,
Yeah.
try to demystify some terms, highlight essential strategies, and even point out common pitfalls. All to give you a shortcut to really being well-informed about this hidden language of chemical reactions. Think of it as a guided tour through the molecular dance floor.
Yeah, that's a good way to put it. And it's important to clarify, too, that this deep dive will focus almost exclusively on what are called ionic reactions.
Okay.
These are reactions involving charged particles, ions, either as reactants, intermediates, or products. And they represent the vast majority, like 95% of what you'll typically encounter in your organic chemistry journey.
Got it. 95%. So let's set the stage for this electron dance then. We've used curved arrows before, right? Especially with resonance structures.
They have.
But you're saying there's a fundamental difference in how we use them in mechanisms. What's that crucial distinction we need to be clear on right from the get-go?
This is such a critical point. In resonance structures, those arrows were essentially just conceptual tools.
Okay.
They showed us electron delocalization within a single molecule, right?
Yeah.
But the electrons weren't actually like moving from one atom to another in a physical process. They were just spread out.
Right, like a hybrid picture.
Exactly. But in mechanisms, those curved arrows mean something totally different. They represent the actual physical movement of electrons. Electrons really are moving during chemical reactions.
Actual movement.
Actual movement. And because of that, it's perfectly okay. It's even necessary sometimes to break a single bond during a mechanism.
Which was that big no-no for resonance.
Precisely. A big no-no there, but it's absolutely central to understanding reactions here.
That makes perfect sense. Like resonance shows a snapshot, but mechanisms show the whole movie of electron movement.
That's a great analogy.
So if electrons are really on the move, let's unpack this and meet the main characters in these electron-moving dramas. Who's doing the moving, who's accepting, who gives, and who takes.
Okay, so at the heart of most of these ionic mechanisms are two fundamental players, nucleophiles and electrophiles.
Right.
Let's start with nucleophiles. Plainly put, a nucleophile is an ion or a compound that is capable of donating a pair of electrons.
Electron donors.
Exactly. Think of them as electron-rich species, always looking to share those electrons. And they come in a few common forms. You've got your negatively charged ions with lone pairs, like the hydride ion, H, or hydroxide, OH, even iodide, I.
Okay.
Then there are neutral compounds that have lone pairs, things like water, H2O, or alcohols, ROH, ammonia, NH3. But what's really interesting, and sometimes overlooked, is that even pi bonds, those double or triple bonds, can act as nucleophilic centers.
Really? Pi bonds too?
Yeah, because they are regions in space of high electron density. The chapter actually highlights an example where a single compound might have both a lone pair on an NH2 group and a pi bond, and both can act as nucleophilic centers.
Wow, okay, so if we have electron donors, the nucleophiles, then we must have electron acceptors in the reaction too, right? Someone's got to take them.
Exactly. That's where electrophiles come in. These are compounds or ions that are, well, poor in electron density.
Electron-poor.
Electron-poor, which is precisely why they get attacked by those electron-rich nucleophiles. You'll often see carbon atoms that are electron-poor, what we sometimes call delta plus.
Oh, no, that partial positive.
Exactly, due to something called induction. Like when carbon is attached to a more electron-negative atom, say a chlorine, which pulls electron density away.
Okay.
Or they can be electron deficient because of both induction and resonance, like the carbon in a carbonyl group, that CO bond. And a prime example of an electrophile you'll see constantly are carbocation intermediates. These have a full positive charge right on a carbon atom.
Okay, those are definitely electron-poor.
Very much so. And the chapter shows a clear example. a chloride ion, acting as a nucleophile, attacking one of these carbocations, the electrophile.
So the key here for our listeners, really, is as you encounter new molecules, try to quickly spot where the electron density is rich.
The nucleophilic centers.
And where it's poor, those are your electrophilic centers. It's like finding the poles of a magnet that will attract each other.
Exactly. Identifying those centers is step one.
Okay, here's where it gets really interesting and honestly a bit confusing sometimes for students. We have these two terms that sound kind of similar but measure totally different things. Basicity and nucleophilicity.
Yes, this is a huge source of confusion. It's really important to untangle them.
So what's the critical distinction?
Okay, let's define them clearly. Nucleophilicity. That's a measure of how quickly a nucleophile will attack an electrophile.
How quickly?
Yes, it's about speed, the rate of the reaction. So we call it a kinetic phenomenon. It's all about the journey of that electron pair, how fast it gets there.
Okay, kinetics. Got it.
Then there's basicity. This is different. It's a measure of the position of equilibrium for an acid-base reaction.
Equilibrium.
Right. It's about how strongly a base holds onto a proton at equilibrium. So it's a thermodynamic phenomenon. It's not about how fast anything happens. It's about the final balance, the destination of the proton, if you will. Even though proton transfers themselves can be super rapid, basicity itself is about that equilibrium position, not the speed.
Okay, so kinetics versus thermodynamics. And this distinction leads to some, well, pretty surprising examples that really highlight why this matters and probably why they trip people up.
Oh, they certainly do. Take the iodide ion. Okay. It's actually among the weakest known bases.
Weak base?
Very weak base. Yet it's also one of the strongest known nucleophiles.
Whoa, okay. Why the difference?
Well, think about it. As a base, its negative charge is spread out over a pretty large volume, right? Iodine's big.
Yeah.
That makes it highly stabilized, so it's not very eager to grab a proton.
Makes sense.
But that same large size makes it highly polarizable. Its electron cloud is kind of soft and squishy.
Right, you mentioned that.
Which means its electron density can easily distort and shift to make a really effective nucleophilic attack. It's very good at reaching out and forming that new bond quickly.
Okay, so weak base, strong nucleophile. What about the flip side?
Good question. Consider the hydride ion, H. It's a very strong base, very unstable, desperately wants to grab a proton.
Okay, strong base.
Yet, it's described as a weak nucleophile.
Weak nucleophile. Why?
Because hydrogen is the smallest atom. Its electron cloud isn't very polarizable. It's not good at distorting to form those new bonds with other electron-deficient centers. It really just prefers to snatch a proton. That's its main game.
So it's true that in many cases, like nucleophilicity and basicity do kind of track together.
Yeah.
Like water is weak for both, hydroxide is strong for both.
Yes, absolutely. They often parallel each other.
But what you're really emphasizing is that the main difference is their job at that moment, their function.
Precisely. It's about the job they're doing in a specific step. A hydroxide ion, or even water, can totally act as a nucleophile in one step, maybe attacking an electron-deficient carbon. Right. Yeah. And then in a later step of the same mechanism, it can switch roles and act as a base, maybe pulling off a proton.
Oh.
The chapter gives a great example with an ester reaction. Hydroxide first attacks the carbonyl carbon, that's a nucleophilic attack. But then later, an intermediate needs deprotonating, and hydroxide comes back as a base to do that job. Water can do the same thing too.
So this raises a really practical question then for anyone trying to draw these mechanisms. In any given step, how do you know? Is it acting as a base or a nucleophile? How can you tell?
It genuinely just comes down to what it's attacking.
Okay.
Follow the arrow. If the arrow starts from your species and points to a proton, H+, it's acting as a base.
Got it.
If that arrow points to an electron-deficient atom, like a carbon that's delta plus, or has a full positive charge, then it's functioning as a nucleophile.
Follow the arrow.
Simple enough.
Follow the arrow. All right, so we've met the players, nucleophiles and electrophiles. We get the crucial difference between basicity and nucleophilicity. Now let's talk about the alphabet of mechanisms, how these players actually move around. You mentioned earlier that just like there were, 5 patterns for resonance structures?
Right.
For ionic mechanisms, there are only 4 fundamental patterns for pushing arrows. That sounds manageable.
It really is. Master these 4 and you basically have the core language down. It makes drawing mechanisms so much less intimidating.
Okay, let's break them down. What's the first one?
Okay, first up, nucleophilic attack. This is exactly what we've been discussing.
Right.
It's where a nucleophile, that electron-rich species, attacks an electrophile, the electron-deficient one. When you draw the arrow, remember, It starts from the electron source, the lone pair, or the pi bond on the nucleophile.
Okay.
And it points directly to the electron-deficient atom on the electrophile. That shows where the new bond is going to form.
Makes sense. Usually just one arrow.
Usually one curved arrow does the job, yeah. But sometimes, especially if a pi bond is the nucleophile doing the attacking, you might need more than one arrow just to show all the electron movement needed for that single attack event. But it's still one event. Nucleophilic attack.
Got it. Pattern number 2.
Number 2 is proton transfer. Again, pretty much what it sounds like.
Base takes a proton from an acid.
Exactly. A base deprotonates an acid. Now, here's the crucial detail, and the chapter points this out as a common mistake. It always requires at least 2 curved arrows.
Always 2. Why?
Because you need one arrow to show the base attacking the proton, and you
Wow.
need a second arrow to show the electrons in the bond that held the proton collapsing back onto whatever the proton was attached to, forming the conjugate base, usually as a lone pair.
You have to show where those bonding electrons go.
You absolutely do. Forgetting that second arrow is a really common error. And just like with nucleophilic attack, it's worth noting a pi bond can also act as a base here, attacking a proton.
Okay, 2 patterns down. Nucleophilic attack, proton transfer. What's third?
Third pattern. Loss of a leaving group.
Okay.
This is when a group basically gets ejected from the molecule, and importantly, it takes its bonding electrons with it.
It just leaves.
It just leaves. Now, what makes a good leaving group?
Yeah.
Generally, they have to be stable on their own once they've left. And that usually means they are weak bases.
Like iodide again.
Iodide is an excellent leaving group because it's a very weak base, very stable as I. In contrast, hydroxide OH is a strong base, right?
Right.
So it's a very poor leaving group. It generally won't just pop off on its own. Sometimes the leaving group doesn't fully detach. It might remain kind of tethered to the molecule, like if an alcohol leaves to form a carbocation, but it's still the same fundamental pattern of electrons leaving with a group.
Okay, that makes sense. Good leaving groups are weak bases. And the fourth pattern.
Finally, number 4 is rearrangement. Now, there are different kinds, but for this course, you'll mostly see what's called a carbocation rearrangement. This is basically characterized by a change in the location of the electron deficient center, usually that positive charge on a carbon atom moving somewhere else within the same molecule.
The positive charge moves.
The positive charge effectively moves. We're actually going to dive deeper into this one in just a minute because it's super important.
Okay, great. So we've got these 4 fundamental moves.
Yeah.
Nucleophilic attack, proton transfer, loss of a leaving group, and rearrangement. What does this mean for putting them together? Are reactions just one pattern, or...
Great question. No, rarely is a reaction just one pattern. Any complete ionic mechanism is really just a particular sequence of these arrow-pushing patterns.
A sequence.
A sequence. For example, you might see a reaction called an SN1 reaction.
Heard of those?
Yeah, it's a type of substitution. Some SN1 reactions involve a sequence that goes first, maybe a proton transfer, then loss of a leaving group, then a nucleophilic attack.
Okay, step by step.
Exactly. And what's really powerful about seeing reactions this way through these patterns is that it kind of unifies seemingly different reactions. You start to see, oh, this reaction uses the same first 2 steps as that other one. It builds connections.
And sometimes, I think you mentioned, things happen really fast, so maybe 2 patterns happen in one go. A concerted process.
Exactly. In a concerted process, 2 arrow-pushing patterns are drawn in a single step. They happen simultaneously.
Like what?
Well, a classic example is the SN2 reaction, another substitution reaction. In SN2, the nucleophilic attack happens at the exact same time as the loss of the leaving group.
Push and pull together.
Push and pull together, exactly. Both electron movements happen in one fluid synchronized step. And one more really crucial point the chapter warns about, another common pitfall.
Okay.
Be careful. Resonance structures are not steps in a mechanism.
Right, you said that earlier.
I know, but it bears repeating. They don't represent any physical process, any actual reaction step. They just show electron delocalization within one structure. Mechanisms are about actual bonds breaking and forming over time. Big difference.
Got it. Resonance is static, mechanisms are dynamic.
Okay, let's zoom in on that 4th pattern you mentioned. Carbocation rearrangements.
Mm-hmm.
You said these are fascinating and crucial. What's going on with these short-lived intermediates?
Yeah, carbocations are, just like you said, short-lived intermediates. They're very fleeting. You definitely can't be stored in a bottle or anything like that.
Right.
If you picture an energy diagram for a reaction, the kind with humps and valleys.
Yeah, the reaction coordinate diagrams.
Exactly. Each hump on that diagram is a transition state for a step, and each valley is an intermediate, like our carbocation.
Okay.
And the hump of highest energy, the highest peak on that diagram, that represents the rate-determining step. That's the slowest step, the bottleneck that controls the overall speed of the reaction. Okay, and where do carbocations usually sit on that diagram? High energy, low energy.
Definitely higher energy. The chapter makes a point that a carbocation intermediate is significantly higher in energy than an oxonium ion, for example.
An oxonium ion. That's oxygen with a positive charge, right?
Yeah.
Like in protonated water or alcohol.
Exactly. And why is the carbocation higher in energy? Because that carbon atom with a positive charge, it only has 6 electrons around it. It lacks an octet.
Unstable.
Inherently unstable. An oxonium ion, even though it has a positive charge on oxygen, that oxygen still has a complete octet. So carbocations are definitely unstable, high-energy intermediates.
So they're fleeting, high-energy spots.
Yeah.
But they're not all equally unstable, are they? I remember something about stability trends.
That's absolutely true, and this is key to rearrangements. There's a very clear carbocation stability trend. Tertiary carbocations, where the positive carbon is bonded to 3 other carbons, are more stable than secondary ones, which are bonded to 2 carbons, which are more stable than primary ones, bonded to just 1 carbon. And methyl carbocations, just CH3 plus Z, are extremely unstable.
Tertiary, secondary, primary methyl. Got it. Why is that?
The main reason is something called hyperconjugation. It's a bit complex, but basically the electrons in nearby carbon hydrogen or carbon sigma bonds can kind of overlap slightly with the empty p orbital on the carbocation carbon.
Okay.
This helps to spread out that positive charge just a little bit, stabilizing it. The more adjacent CH or CC bonds there are, the more hyperconjugation, the more stable the carbocation. Hence, tertiary is best.
Makes sense. More neighbors helping out?
Kind of like that, yeah. And crucially, carbocations are also significantly stabilized by resonance.
Resonance again?
Resonance is always important. Think about allylic carbocations where the positive charge is next to a double bond, or benzylic carbocations next to a benzene ring. In these cases, the positive charge isn't stuck on one carbon, it's spread over 2 or more locations. It's delocalized through resonance structures.
Right, drawing those extra arrows.
Exactly. And that delocalization makes them much, much more stable. In fact, the chapter points out that a tertiary allylic carbocation is even more stable than a regular tertiary carbocation because it gets both tertiary stability and resonance stabilization.
Wow. Okay. So stability matters a lot. Which brings us to the big question. When do these carbocations actually rearrange? Does it just happen sometimes?
Not randomly, no. There's a golden rule here. A carbocation will rearrange whenever it can become more stable by doing so.
Whenever it can become more stable.
Yes. So if you have a secondary carbocation, and a simple shift can turn it into a more stable tertiary one, it'll likely happen.
Well,
or even if you have a tertiary carbocation, but a shift could turn it into a, say, tertiary allylic carbocation. That resonance stabilization is a big driving force, so it'll probably rearrange for that extra stability too. It's always seeking that lower energy state.
Always downhill energetically.
Yeah.
So how do they do it? What are these shifts?
There are 2 common types of shifts you absolutely need to know. The first is called a methyl shift. This is where an entire methyl group, H3C, along with its bonding electrons, literally migrates from one carbon atom to the adjacent positively charged carbon.
The whole CH3 group moves?
The whole group, electrons and all. The chapter uses a neat analogy. Think of the positive charge as a hole in the ground. When the methyl group moves over, it kind of plugs the hole where the positive charge was.
Right.
But in doing so, it leaves behind a new hole, a new positive charge where the methyl group used to be. So effectively, the positive charge has moved location, presumably to a more stable spot.
I see. The charge moves by the group moving. What's the other type of shift?
The second type is very similar. It's called a hydride shift.
Hydride?
Like H?
Exactly. It's a hydrogen atom migrating with its 2 bonding electrons essentially as H, a hydride ion. Just like a methyl shift, the hydride moves from an adjacent carbon to the positively charged carbon, plugging that hole and creating a new positive charge where the hydride came from.
Same idea, just a hydrogen instead of a methyl group. Same fundamental idea, yes. Both are ways for the molecule to rearrange itself, to put that unstable positive charge in a more stable location if possible.
So the practical advice here seems really clear then. Whenever you propose a mechanism involving a carbocation intermediate, You absolutely must analyze its structure and figure out if it could rearrange to something more stable.
You have to check. Every single time you form a carbocation in a mechanism, you pause and ask, can it rearrange?
And the chapter has an exercise that walks you through this, right? Looking at a secondary carbocation.
Yes, it shows you how to look at the atoms adjacent to the positive charge. Could a hydride shift from an adjacent carbon create a tertiary carbocation? Could a methyl shift do it? You have to identify which potential shift, if any, would actually lead to a more stable carbocation tertiary, or maybe one stabilized by resonance.
It's not just about any shift, it has to be a stabilizing shift.
Correct. No point rearranging to something less stable. It's all driven by stability.
Okay. We've built up the tools, we've met the players, learned the patterns, even dove into rearrangements. Now, let's connect this all back to the bigger picture. Why are mechanisms so important? Beyond just showing electron arrows, what's the ultimate payoff for mastering them?
This really is the so what of mechanisms, isn't it? And it's huge. The key takeaway is that the proposed mechanism must always explain the experimental observations.
What you actually see happen in the lab.
Exactly. And this includes two critical aspects of the outcome: the stereochemical outcome and the regiochemical outcome of a reaction. If your mechanism doesn't explain those, then your understanding is incomplete, and you're probably just memorizing facts without the why.
Okay, let's define those terms clearly. First, stereochemical outcome. What does that cover?
Stereochemical outcome refers to what happens to the configuration of a stereocenter. You know, those chiral centers with R and S configuration.
Right, the 3D arrangement.
Exactly. Does the reaction create a new stereocenter? Does an existing one get inverted or maybe scrambled? Or if you can form different distereomers, which ones are actually formed? It's all about the 3D shape of the products.
Can you give some examples of how mechanisms explain this?
Sure. Think about those substitution reactions, again, SN1 and SN2. One mechanism, SN1, involves that flat carbocation intermediate. That explains why you often get racemization, a 50-50 mix of R and S products, because the nucleophile can attack from either side of that flat intermediate.
Oh, yeah.
But the other mechanism, SN2, is concerted. The nucleophile attacks from the back as the leaving group leaves from the front. This mechanism explains why you get inversion of configuration and R starting material becomes an S product or vice versa. The mechanism dictates the stereochemical outcome.
Wow, okay. So the mechanism isn't just arrows, it is the explanation.
It is the explanation. Or think about elimination reactions. If you can form stereoisomeric alkenes like cis and trans, the mechanism often explains why the transisomer might be the major product. Or in addition reactions, like that hydroboration oxidation example.
Yeah.
Even though maybe 4 stereoisomers seem possible on paper, you might only observe 2. Why? Because that mechanism involves synaddition. The H and the OH group get added across the same side of the original double bond, not anti-addition. The mechanism dictates which specific stereoisomers form.
That's powerful. Okay, so that's stereochemistry. What about the other one? Regiochemical outcome.
Regiochemical outcome becomes important when a reaction can give products that are constitutional isomers.
Meaning they have the same formula but different connectivity.
Exactly. And the question is, which constitutional isomer predominates? Where do the atoms actually end up connecting?
Like where a double bond forms.
Precisely. In an elimination reaction, if the double bond could form between C1 and C2, or between C2 and C3, which position is preferred? That's regiochemistry. Or back to our hydroboration oxidation example. The regiochemistry question is, where does the OH group end up? Does it add to the more substituted carbon of the original alkene, or the less substituted one? In this specific reaction, the mechanism explains why it ends up at the less substituted position. Again, the mechanism has to justify the observed experimental result, the regioselectivity.
This is huge, because honestly, students often just try to memorize all these outcomes, right? SN1 gives racemization, SN2 gives inversion, hydroboration is anti-Markovnikov synaddition. It feels like a giant list of rules.
It can absolutely feel that way. It's overwhelming.
But the chapter is suggesting a much more powerful and maybe even easier approach in the long run.
It really is. It's a total shift in perspective, and it's a game changer. The book makes this point very clearly. If you focus on understanding the proposed mechanism for each reaction, with a complete understanding of how that mechanism justifies both the stereochemical and the regiochemical outcomes,
right,
then you will find that you will remember the details of each reaction more easily, without much need for memorization.
Ah, so the mechanism becomes the organizing principle.
Exactly. It provides the underlying logic. It connects the how of the electron movement with the why of the experimental outcome. Once you see that connection, all those seemingly separate facts start to click into place.
That sounds much better than rote memorization. And the chapter actually gives an action plan for really getting there, for mastering these mechanisms.
It does, and it's incredibly practical advice. It says, for each mechanism that you encounter, you should be able to draw the entire mechanism on a blank piece of paper.
Just draw it out cold.
Draw it out cold. Arrows, intermediates, everything. But then, and this is the crucial follow-up that really cements it,
Okay.
then wait a day and do it again when it is not fresh in your mind.
Spaced repetition.
Exactly. Practice it again later. And keep practicing until you can draw the entire mechanism, without mistakes, on a blank sheet of paper. It's that active recall, spaced out over time, that truly solidifies the understanding and moves it from fragile short-term memory to robust, deep comprehension.
This discipline, the chapter promises, will greatly enhance your understanding and, yeah, probably your grade too.
Definitely.
It's like learning, I don't know, scales on a piano or something.
Yeah.
You don't just read the music, you have to practice until it becomes second nature.
That's a perfect analogy. You internalize the patterns.
Well, we've certainly taken a deep dive today into this fascinating world of reaction mechanisms. We've unpacked their definition, identified the key players, those nucleophiles and electrophiles, clarified that tricky distinction between basicity and nucleophilicity, and mastered the 4 fundamental arrow-pushing patterns. We explored the twists and turns of carbocation rearrangements, and maybe most importantly, we've seen how truly understanding mechanisms unlocks the why behind every experimental observation, from stereochemistry to regiochemistry.
Yeah, mechanisms aren't just, abstract diagrams scribbled on a page. They're truly the dynamic language of chemical transformation. They reveal this elegant, logical choreography of how molecules interact, how they break apart, how they rearrange themselves in these predictable, understandable ways.
It really is like seeing the hidden dance of electrons that drives all the chemistry happening around us and inside us.
It is.
And think about it. Once you understand how those electrons are moving, how those tiny charges in electron-rich spots dictate the whole dance of the atoms, the entire picture of organic chemistry just starts to click, doesn't it?
It really does.
It's like learning the rules of chess and suddenly seeing the strategy, not just the individual pieces moving around. It truly transforms your understanding from just memorizing facts to having genuine insight. Well, thank you so much for joining us on this deep dive today. We really hope this exploration of mechanisms helps you see that hidden dance of electrons in a whole new light.
Yeah, keep that curiosity burning. Keep asking how and why about the reactions you encounter. That's honestly the real key to mastering organic chemistry and, understanding the world at a deeper molecular level.
Couldn't agree more. Until next time, keep exploring the incredible world around you.